Hi guys, this is Mrs. Gassler, and in this video we're going to talk about acids and bases, as well as their definitions, how we define those and a couple of different ways to look at them. We will not be talking about pH scale in this video. You'll have to watch another video to learn more about the pH scale. So we're going to go ahead and get started. If you want to pause and make your note paper look like this, and then get started, you certainly can. I'll leave this here. Alright, so here's what we're going to do. First off, we're going to talk about the properties of acids and bases. First, acids. Actually, we'll compare them both at the same time. Okay, acids usually taste sour. In fact, the reason sour candy tastes sour is because they've covered it in an acid that makes it taste that way. Bases, on the opposite side, taste bitter instead, and sometimes people describe those as tasting metallic. Something that acids do is they turn blue litmus red. They don't turn red litmus any color. And bases on the other side turn red litmus blue. Okay, blue for basic, if you can remember that, that might help you out to keep those two straight. Another thing that acids have in common with bases, sort of, is an acid can neutralize a base, where a base can neutralize an acid. That means that neither the solution, if you mix an acid and a base together, the solution that you get in the end will not be acid or base, but somewhere in between. And then something that's not exactly common or whatnot, bases tend to feel slippery. So if you get a base on your fingers, if you've ever accidentally gotten bleach on your hand, you remember how smooth it makes your fingers feel. That's a sign of a base. And acids can dissolve metals. Bases don't dissolve metals, but acids do. Okay. So we're going to talk about some definitions of acids and bases, and there's two guys that we're going to be focused on in our unit. There's a couple of other definitions of acids and bases, but they're similar, just a little bit different. We're going to talk about this Arrhenius and bronsted-lowry acids and bases. So we're going to compare them kind of next to each other. Okay. So in an acid, according to Arrhenius, these guys produce H+ ions when you put them in water. Okay, the number of H+ ions increases. We'll talk about what that means here in a little bit. Bronsted-Lowry says that it kind of does the same thing, but they call it a proton donor. Okay, so if something donates a proton, then it is an acid base. But the proton that it's donating is an H+. Okay, so they're kind of doing the same thing here. You'll see the real difference. They're kind of the same as far as acids go, producing the H+ ions and giving up a positive ion there. With the bases, they're a little bit more different. So here we go. With a base, Arrhenius says that they produce OH- ions. It's called a hydroxide ion. When you mix it into water, there ends up being more OH+ ions in there than not. And the way Bronsted describes these is also the opposite of his definition. It is a proton acceptor. Okay, that means it takes the H+ ion. Okay, so slightly different thought process here, but they're kind of similar. We'll talk about that more in a little bit. When we talk about acids and bases, according to the Arrhenius one, what happens is that an acid plus a base, when they mix, they form a salt and water. And something you need to know about the salt is that it's not necessarily table salt. It could be any kind of salt. In fact, a salt is sometimes defined as what's produced during an acid-base reaction. So salt and water. So we've got our H2Os there. When we talk about a Bronsted-Lowry acid and a base, what's really interesting about those is that it depends on what you mix it with. It depends on what it's mixed with. And what happens is that sometimes sometimes a substance is an acid, and in other situations it's a base. So sometimes it's an acid, and other times a base. The same substance could be one or the other, and the term for that is called amphoretic. When it can be either an acid or a base, depending on the situation, it's called an amphoretic. So water is a good example of an amphoretic. Sometimes water is accepting the proton, and sometimes it's donating the proton. So sometimes it's the base, and sometimes it's the acid. So now the reason all this happens, and the reason these definitions kind of work, is because of this thing called the auto-ionization of water. And that's literally what that means is that in water, water molecules dissociate too. Water molecules dissociate and recombine, so they're coming apart and together, and sometimes they do this interesting thing where if you have two water molecules, okay, they can turn into this thing here. One of those hydrogens leaves one of these waters and joins the other one, and then the other one is left missing a water. Okay, now this thing right here is called the hydronium ion, and the hydronium ion is used kind of interchangeably when we talk about things with the H+. So if you hear somebody talking about the H+ concentration or the hydronium concentration, they're talking about the same thing. This guy over here is the hydroxide ion. They both have the same charge, so these things stick together, but they're combined differently. So we have some exchanges here. Now in water, it also goes the other way. The hydronium loses its hydrogen and it goes back to oxygen. And so in water you have kind of an even amount of everything, and so that actually is what makes water neutral. In this situation, here's a good example of this amphoretic here. So let's see if we label them here. This one is maybe it's the one that's gaining the hydrogen. That means it's a proton acceptor, which makes it a bronsted-lowry base. This one over here, though, is losing the hydrogen, which makes it the bronsted-lowry acid. And then on the other side, this one is giving up the hydrogen when it loses it, so that one is the bronsted-lowry acid, and this one is the base. It's an interesting situation. That concept there of those going together in like a pair is called an acid-base conjugate, which we'll talk about later on in another video. Okay, so that's pretty much the generic what you need to know about acids and bases. Again, there's more things about measuring the acids and the bases that we'll talk about in later videos. If you have any questions, make sure you ask your teacher. Thanks for watching. Hi guys, in this video we're going to be talking about pH and pOH and what they mean about acids and bases. Just from a what is it kind of perspective. We'll do some calculations at another time. Alright, so I've got some kind of pre-filled out notes here. If you wanted to take a minute and get those to look like mine, this is kind of what they look like, and there's nothing below this right here. You can stop it and make that look that way. And then I'm going to go ahead and fill in some things. So we talked about auto-ionization already, and remember that's when our water, when it's just together with other water molecules, this thing happens where it can turn into an ion, but it has an equal amount of the other ions, the positive and negative, so the whole thing ends up staying neutral. And when we talk about a neutral substance, real fast, to talk about this, remember this is the hydronium, and this is the hydroxide ion. That's an ion too. The hydronium comes because this one of these guys loses an H+, and it's just kind of floating around, and it sticks to this other guy, and so it becomes the hydronium ion. So it used to be attached to this guy, but it left, and it joined up over here. Okay, so that's what happens. In solutions, we talk about the concentration of these things, and the way we write this down looks like this. So you might see it like this. That means literally the concentration of the hydrogen ions or hydronium. You can use those interchangeably here. They'll be the same thing. And then if you see OH minus in these little brackets, that is the concentration of the hydroxide ion. Okay, hydroxide ion. And so when we talk about solutions and whether they're acids and bases, and we're talking about the pH scale too, we're talking about the concentrations of these things. So in a neutral solution, like water, the amount of hydrogen that's floating around there is the same as the concentration of the hydroxide ion. So it's the same, but when you put something into the water and it dissolves, interesting things happen, and you end up having either more hydrogen or more hydroxide. And so we'll talk about both of those. So if you put something in there and the H30 plus, that hydronium ion, if that concentration increases, whoops, I forgot the N. If that increases, so, and again, we're talking about the H plus ion here, okay? If that increases, we say that it's an acid. So in an acid, the hydrogen ion there's more of it than the hydroxide ion. So we write it like that. So that's an acid, okay? When we're talking about bases, we end up with more of the hydroxide ion, and the hydroxide ion doesn't have to come out of anything. It could be in the water. You could have something that steals away the hydrogens, leaving more of this just hanging around too. In our, what do you call it? Well, it works either way. If this concentration increases, okay, then what we end up having is a base. So we say that our neutral solution, they're equal. Our acid, the hydrogen is more, and in our base, the hydroxide is more. So when we're talking about pH, we're literally talking about the kind of, it doesn't really help to think about it as the percent hydrogen, but we're talking about the hydrogen concentration. The reason it doesn't help to think about it is because it's the opposite, okay? So if our pH scale looks like this, we also measure this other thing called the pOH, which is the same thing, but we're talking about the hydroxide ions instead. So they go backwards. You see the pH goes up while the OH goes down, but they have the same scale. Okay, they have the same amount. Let me move this paper out of the way. And right smack dab in the center is neutral. So regardless of whether you're talking about pH or pOH, 7 is neutral. Okay. On the pH scale, 0 is this is our acid end, and this is our base end over here. Let's keep the words the same orientation there. Okay. And anytime, and I don't know exactly where the line is, but somewhere over here, this is where your strong acids are. Okay, and this is where your strong bases are, which we'll talk about those again in another video. And this is where your weak bases are, and this is where your weak acids are. The closer they are to 7, the more weak of an acid or base they are. And it doesn't matter which scale you're looking at, it's still the same. So if you'll notice on our pH scale, acids have the low numbers and bases have the high numbers. But on the pOH scale, it's exactly the opposite. Okay, remember that, and this is counterintuitive also, so you'd think, well, it has more hydrogen, so it must be an acid, so the pH would be high, but the pH is kind of like the inverse of the hydrogen concentration. It's not exactly an inverse, but it's kind of that way. But the lower pH means that there's, and I'm going to write this in a different color, okay? Here we have a high concentration of the hydrogen ions and a low amount of the OH minus ions. And here it's a low amount of the H plus. I didn't mean to put that in bracket. The bracket goes over there. And here we have a high amount of the OH. Okay, so you can see how they're kind of flip-flopped back and forth, and it might be counterintuitive, and whatever you need to do to be able to remember the organization here on the pH and the pOH scale is what you need to do. But one thing I do want to tell you is that no matter what scale you're looking at, whatever information it gives you, when you add them together, it always equals 14. Okay, 14, 14, 14, 14, 14, 14, 14, 14, right? So if it gives you pOH and you're more familiar with the pH scale, just find the difference between it and 14 and then answer all your questions based on the pH scale. That's also an easy thing to do, okay? So that's just a little bit about the pH scale. In a later video, we'll calculate with it. Ooh, it's very exciting. Okay, ask your teacher if you have any questions. Thanks for watching. Hey guys, this is Mrs. Gassler, and in this video we're going to talk about the difference between strong and weak, and we're going to talk about both acids and bases at the same time here. Okay, so I've got, I've got some formulas written down if you wanted to jot those down real fast so that you can be ready to go when I get there. We're going to talk about strong and weak kind of at the same time here. Okay, so remember, neutral is 7 on the pH or pOH scale is neutral. So if it's at a 7, that's neutral. It is not an acid or a base. So if it is weak, then it's going to have a number that is close to 7, whether it's above or below. On the pH scale, above 7 on the pH scale is going to mean it's a weak base, and if it's below 7 on the pH scale, then that means it's going to be an acid, but as long as it's close to 7, then we would say that it's weak. Strong acids are going to be on the other side, that they're going to be far from 7. Okay, same idea though. Above is still a base and below is still an acid, but it's farther away from 7 on the pH scale. So if you have pH information, that's a good way to know if it's a strong base or a strong acid. And again, close to 7 is weak, far from 7 is strong. Now, when we talk about what makes it, wow, I can't really tell that that's blue. Interesting. Okay. When we talk about what makes it strong and weak, we have to think about what's happening within the solution. So when we dissolve our substance in a weak solution, so remember that auto-ionization, I'm going to draw that right in here, auto-ionization, that H2O gets together with that other H2O, and we get some hydronium, which is the positive, and we get some OH, which is the negative ions that are floating around. In water, sometimes not everything breaks apart. So I can't think of any off the top of my head, but when you have a weak base, only some of the particles, and I'm going to use the word dissociate, only some of the particles dissociate to make some of the hydronium, some of the hydroxide. So that's actually why it has a closer to 7, because the ratio of the hydronium to hydroxide, I don't know if you've ever driven a stick shift, so remember how they have to add up to 14. And the closer you get to them being the same, that's when they're neutral, and when you have more of one or more of the other, that's when it's an acid or a base. So if this is my hydronium hand, the H plus, oh, I should have made that the OH one because I can't really write with my left hand. Here's my OH. You're going to have to use your imagination. That's an H, and there's a minus, okay? So as my H plus increases and my OH goes down, then I have something. And if I have, that would be my acid, and if I have more of the OH, then this is my base. But if it's a weak base, then I only have a little bit more. I only have a little bit more for my weak base and a little bit more for my weak acid. So it's not completely dissociating, so I don't have as much of the H plus, ignore that 3, or the OH minus. Okay, now remember, this would be my acid and this would be my base. Okay, so if I don't have a significant difference in between them, then it's a weak acid or a weak base. Okay, on the other side, with my strong acids, all of it dissociates. Okay, that means I have the most possible amount that I could have. I have the most of my hydrogen concentration or my hydroxide concentration. So remember, with my weak base, here's neutral, here's my weak acid, here's my strong acid, here's my neutral again, here's my weak base, here's my strong base, so that the difference between the amounts of hydroxide ion and the hydrogen ion are different. So now there's some, and this is all I can tell you, is that you're going to have to memorize a few things here, but it's kind of easy. So here's your strong bases and your strong acids. Okay, so we're going to talk about our strong bases first. The first thing you might notice is they all have that OH there. That's how you end up with more OHs in the mix. Okay, this is lithium hydroxide. You're also learning some naming here. These are easy to name because you just take the metal ion and stick the OH on it. Okay, this is sodium hydroxide. This is potassium hydroxide. Oh, now I can tell it's blue. This is SR is for strontium. It's not one of those, what do you call it, short metals. It's one of the tall ones, so I don't have to put a Roman numeral, but this is strontium hydroxide. This is calcium hydroxide. and this is barium hydroxide. Now, the way this works is if it's not in this list, it's a weak base. Okay, these are the strong bases, the really strong bases. They're on our list there because they're very strong and we know it. Okay, so these are our strong bases that we keep track of. These are our strong acids, and you'll learn a little bit about how to name acids too. These are actually separated out here in a nice way. This is, you won't see this until advanced, but this is proficient right here. When you have just a single atom attached to a hydrogen, remember that all the acids have a hydrogen in front. This becomes hydro, and then you tack on the name, but you change the "ene" to "ic", and then you add acid at the end. So this is hydrochloric acid. We're going to do the same thing here. This is hydro, and that's bromine, so it becomes bromic acid. This one is hydro, that's iodine, so it becomes iodic acid. And we do something similar here, but definitely not. This is nitric acid. This is this is the high one, right? Perchloric acid, which you'll learn about how to name that one later. And this one is sulfuric acid. Okay. So again, it's better to memorize the formulas than the names because you don't have to know how to name the formulas yet. But these are our strong bases. So if this is in your list, it's a strong base, and these are our strong acids. And if it's not on the list, we don't consider it strong. So if you have any questions, make sure you ask your teacher. Thanks for watching.